Hello everyone, this is Dilip. In this video, let's take a look at neural networks and how they can help us in solving nonlinear hypothesis problems. Let's take a look at neural networks. This is the neurons that exist in our brain and all over the body. As you know, neurons exist all over the body, and each of these is called a neuron. As you can see, the neurons communicate with each other with layers called axons, and these are connected with dendrites. And when any of the information comes to each neuron, it will do some processing for the information and it will pass on to the next neuron. And it will pass this information using electrical signals called synapse. The intuition I want to give from this picture is each neuron is contributing in some way for processing the information. It need not be that the information which is passed to this neuron is final and this has to take a decision. It can pass the information to this neuron, and based on this information, it can take new decisions. And this neuron doesn't need to rely on the original information. It can rely on the information passed by the previous neuron, which is already pre-processed. So if we are moving our hand or moving our leg or doing anything with our fingers, it has to come from the brain in the form of electrical signals called synapses, and the nervous system present in our hands or legs responds as per the command from the brain. This is the simplest neural network we'll see, where we only have a single neuron taking inputs from the input features. So these three variables, using the parameters given, we get our hypothesis, which is again sigmoid is done for this. So our hypothesis, based on the numbers shown here, we can show as theta1 x1, theta2 x2, theta3 x3, and additionally we can have x0, which is usually 1, we put it, and additionally we can have a theta0 parameter as well for this. But we'll see in neural networks this bias parameter usually doesn't matter much, because as we pass through layers of neural network, we'll see like we already do the pre-processing, so this bias parameter becomes less important, but we can include it. So here you can see a neural network where I have added one more layer, and we'll see only with this one layer so that it will be easy to derive our hypothesis. So given the input features x1, x2, and x3, what we are doing is any of this neuron in the between layer, it will have an hypothesis, and we take a sigmoid of it to get the value of the neuron over here. So a hypothesis will look like this. And if we take A11 here, what we are seeing here is a hypothesis which is like this. So this first parameter is coming from here, and the second parameter is coming from the second neuron, and the third parameter is coming from the third neuron. And here you see the parameter, I have put some notation. This 1 in the superscript, it indicates it is for the first layer. So all the theta parameters are for the first layer. And the second one, this indicates it is coming from the neuron 1. This 2 indicates it is coming from neuron 2, and this 3 indicates it is coming from neuron 3. And the first one indicates it is the first input from the neuron 1. This indicates the first input from neuron 2. For example, if you take this will be second input from the neuron 2. So this will be theta 2 2. So theta 1 of theta 2 2. So like this. So this way it will help us give a vectorized notation for this, so that our calculations will be easier, just like we have seen in linear or logistic regression. So once we get our hypothesis, we can take a sigmoid of it, and that will give us the value of A11. And in the end, our hypothesis will be sigmoid of this. And you will see the theta superscript became 2 here because it is coming from the second layer. And as you can see, this is the first input of the first neuron. This is the first input of second neuron, and this is the third input of the first neuron. And here also the features, also you will see the variables. We are having the superscript indicates it is from the first layer, and the subscript indicates it is the neuron, like which neuron, first neuron or second neuron or the third neuron. So this way we can see we can derive a hypothesis for neural networks as well. And one more interesting thing I want to show you is this. If you just blank out the input features which are given to us, we will see this hypothesis, it just looks like a normal logistic regression hypothesis. The main difference you can see here, we need not rely on the input features given, which is x1, x2, x3. Instead, we can take on more complex features, A11, A12, A13, to derive our hypothesis. And we will see in future videos how we can derive this, all the parameters for all the layers. Like not only for this layer, we need to derive hypothesis for this layer as well. We will see how to do that in the later videos. So this way of moving forward and calculating the hypothesis is called forward propagation. In the next video, we will see about backward propagation and how to derive the parameters. Some more terminology I wanted to introduce here. Whatever the variables we input, this is on the first layer, we call it, and this we call as input layer. So whatever the initial variables are there, they will come in the input layer. And whatever the in between layers, these are called hidden layers. And output layer is where our final hypothesis will be present. So if it's a multi-class classification problem, you will have a multiple hypothesis. Thanks everyone for watching the video. Bye.